Hello everyone. So welcome to lecture 45. So in the last class we were looking at Onsagers theory, the properties of all these Onsagers coefficients. We said there is reciprocity, which is an important property, and by virtue of we just doing linear theory, linear Onsagers theory, we say that none of these Onsagers coefficients, all these are properties, right? They are not dependent on the forces that we apply. Okay, so that's the first property of all these Onsagers coefficients, and the second property we said is reciprocity should be valid. We said reciprocity is mostly valid, right? So there are some exceptions because we have derived all the Onsagers formulation by assuming Ts dot is just dissipation, right? But turns out that if S is changing with temperature, with time, right. So as some sort of an oscillatory function which can happen in, for example, in neurons or neural systems, such a thing happens, right. Then the validity of Onsagers reciprocity is to be questioned. Then what we get are also not properties that are dissipative in nature, but they do not dissipate. Although they are out of equilibrium, they do not dissipate, right. So these are not thermodynamic properties, but these are non-dissipative thermodynamic quantities, right. So but we said that this sort of thing is is an exception, but we will not look at this in our course, right. So in our course, if I have Ts dot is just power dissipated, right. So Ts dot is just always power dissipated. And if I have power dissipated, I always have IVs or so electrically this is the power dissipated, mechanically the power dissipated is going to be strain rate, which is x dot times capital X times volume, right. So let's put it this way. So this is going to be the this is volume, right. So this is the power dissipated mechanically, and so on and so forth, right. So I can have some magnetic power dissipated, I can have chemical power dissipated, right. So just by virtue of diffusion of atoms around and so on and so forth. Okay, so so the properties ensuing out of power dissipation are very nicely explained by linear response theory, Onsagers linear response theory. And we have seen many examples. We have seen that piezo resistance, we have seen direct properties such as conductivity, thermal conductivity, electrical conductivity, thermal conductivity, creep coefficients, the friction coefficients, all these come directly from Onsagers linear response theory, diffusivities, right. And also the coupled properties such as this thermoelectric properties such as electromigration, right. So all these phenomena, piezo resistance, right. So all these phenomena can also be explained by Onsagers linear response theory, which otherwise is difficult to it's difficult to get all these properties in one generalized framework, right. So that's the beauty of this theory, right. So it can do exactly that. Okay, now let us look at another example, and this is one of the more crucial examples, right. So the case of thermoelectricity, and so let us start with a thermocouple. So what is a thermocouple? A thermocouple is set of two wires. So this is wire A, this is wire B. Both of them are metallic wires. A, B are metallic wires. A can be copper, B can be copper, nickel, some sort of an alloy with copper and nickel, and so on and so forth, right. So both of these are so it's I'm going to form what is called a thermocouple, and thermocouple is used to measure temperature. Okay, so the question is, how are we going to do this? Okay, okay, so I have A, I have B, and so this there is going to be some sort of, this is at let's say room temperature T, and this is at T plus delta T, and I need to measure what this delta T is. Okay, so the two junctions are at different temperatures. All right. Okay, so if the two junctions are at different temperatures, what I am going to do is I am going to connect. I am going to actually not connect these two things, but I am going to connect a voltmeter there. Right. So, both of them are at temperature T, that is okay, but I am going to connect a voltmeter and I am going to not pass any current through this. There is no current, no electrical current, because I do not complete the circuit. Voltmeter has infinite resistance, but I just measure the voltage. From the voltmeter. Okay, so let me, sorry, I cannot undo things here, so let us redo it. So, A is like this and B is like this. Okay. So, A is at, so this junction is at T plus delta T. This is the temperature I want to measure, whereas here I have connected a voltmeter. Again, I cannot be connecting it. Sorry. Last time, I will do it better this time. Yes. And I connect a voltmeter. Yes. Okay. So, voltmeter is in red. So, I am not passing any current. Electrical current J equal to 0, J E equal to 0. Okay. And the idea is I have to generate a voltage or a potential difference between A, so this voltmeter should read something, right. So, I have to generate a potential difference that is proportional to delta T, right. Then I can know the temperature here, right. So, that is how I am going to measure the temperature. So, that is so this is a way of measuring temperature. Okay. So, all right. So, let us go back to our Onsagers, what is the heat. So, we said, okay, so let's write an expression for electronic flux, right. So, flux of electrons is just minus L E Q, right, ln T. This is the thermal force, right, and this is thermal force driving electric current, minus L E E, right. So, this is the electric force, that is the gradient of mu E is nothing but the chemical potential gradient of electrons. Okay. So, this is in wire A. I am just going to write this in wire A, right. Same thing in wire B, but J E A equal to J E B equal to 0. Okay. Okay. So, let us keep that in mind. J E B is equal to minus L E Q B ln T, right. This is between these two corners, right. So, that is what I am going to look at, minus L E E A gradient of mu E in the wire B. This is in the wire A, right, L E B. This is also, and gradient of temperature is going to be the same in both cases, all right. Okay, so that is that. So, if J E equal to 0, what I have is L E Q gradient of ln T equal to L E E. Instead of writing it as minus del mu E B or mu E A, I am just going to write it as del phi A. Okay. This is for A. Okay. And similarly, I have an expression for B, right. So, now I am going to say what is delta phi A. Delta phi A is the change in potential between 1 and 2, right. So, in along wire A, right. So, delta phi A equal to phi 1 minus or phi 2 minus phi 1 in wire A, right. Similarly, delta phi B will be phi 2 minus phi 1 in wire B. Okay. So, let us look at what delta phi A is, and so what I am going to find is V equal to delta phi B minus delta phi A. That is the potential that I am going to generate, right. So, this is the generated potential voltage. Okay. So, now what is so just gradient of phi A is equal to LEQA by ELEE, right, gradient of ln t, correct. So, that is whereas if I actually integrate this with respect to, so if I write what del phi A equal to, that will just be equal to EQA by ELEEA, right. So if I integrate logarithm of something, I just get t plus delta t by t, right. So, I am integrating both sides with respect to the corresponding length of it. Okay. So this is what I get, and similarly delta phi b, this is delta phi, this is not gradient, EQB by ELEEB ln t plus delta t by t. So, this part remains the same. Okay. Now, this is nothing but my sigma b, this is nothing but my sigma a, these are the conductivities if I remember them correctly. So, this is sigma a, this is sigma b, these are the conductivities of A and B, right. Now, I have a potential difference if so V is just delta phi B minus delta phi A. So, that is equal to, in all ideal scenario, t plus delta t by t, right. LEQB 1 over E or by sigma B minus LEQA by sigma A, right. So, this is from, if I know these coefficients, I know what the voltage I am generating, and that is not linearly dependent on delta t, but so if I do some approximations, it will be dependent on delta t, right. So, with approximations, right. So, this is not a linear sensor in all, this is not a linear temperature detector. Okay. Okay. So, now let us go back to this delta phi in one of the wires, right. So, in one of the wires delta phi is given as LEQ by ELEEA. So, these are all Onsagers, sorry, A is the wire that I am considering, ln 1 plus delta t by t. Okay. Now, so that I am just going to expand it, LEE 1 plus so ln 1 plus x can just be expanded as x plus something, right. So, if I just take the linear term, it is just x, right. So instead of 1 plus, so if delta t by t is small enough, I am just going to expand it as ln 1 plus x. Actually, this is going to be x minus x square. Let's write the, for small x, no, the expansion of ln 1 plus x equal to x minus x square by 2 plus x cube by 3 minus and so on, and for small x that reduces to just x. Okay. So, delta phi then is LEQ by ELEE times delta t by t, right. Okay. So, now I have generated some potential by having a gradient in temperature, right. So, if for any single wire, right. So, if I have this is a T1 and this is a T2, right. Now, ideally so how do I understand this? So, I have a wire where this is a T1 and this is a T2. So, if I have a wire where one end is a T1 and the other end is a T2, of course, there is going to be some form of electron convection. If I assume electron just as a gas that reacts to temperature, right. So, electron also has some statistics through which it will react to temperature. The electron distribution here is different from the electron distribution here. So, electron concentration at 2 is different from electron concentration at 1, right. As a result, I generate a voltage. Okay. Let me just write it properly. Electron concentration at 2 is different from electron concentration at 1, and let me not confuse you by writing electron convection. I am just going to say here in a different color that there is going to be electron convection. Okay. All right. So, as a result I generate voltage. Okay. Now, what is the magnitude of this voltage? Delta phi equal to LEQ by ELE delta T by T, right. And so one can actually say delta phi by delta T is equal to LEQ by ELEE, right. Now, assuming that I did not make a mistake in signs, I guess this is all right. ELEE, right. So, there is no minus here. Yeah. So, when I change this, I have an E times del phi. Okay. So, gradient of phi. Fantastic. Okay. All right. No problem. So, this guy, right. So, this guy here is what is called Seebeck coefficient. And rest assured, you can imagine. So, so if I have an electron, a charge depending on the charge carriers that I have, right. So, here comes the sign of the charge carrier, right. So, if I have so for electrons it is coming out as plus E, but for holes or some other form of charge carriers the sign will change, right. So, charge carriers, the type of charge carriers dictate the sign of Seebeck coefficient. Right. So, to understand what sort of charge carriers, so I can do Seebeck measurements to understand the type of charge carriers in my semiconductor, right. So, typically in semiconductors I need to determine whether my semiconductor is N type or P type, right. So, what are the majority charge carriers? So, one, I can do Hall measurement, that we have seen long time ago, that Hall measurement, the sign of Hall voltage or Hall resistance actually tells me what is the nature of charge carrier, and similarly the sign of Seebeck coefficient also tells me what is the nature of my charge carriers, right. So, right. So, to understand whether I have N type carriers or P type carriers, I can either do Seebeck measurement or I can do Hall measurement. Okay. So, so all right. So, that is the Seebeck coefficient, right. So, the point here being the Seebeck coefficient is also derived from just Onsagers coefficients, right. So, Seebeck coefficient are also derivatives, or not derivatives in not in the mathematical sense, but are also derived from Onsagers cross coupling and direct coefficients. So, LEE is the direct coefficient, LEQ is the cross coupling coefficient. Direct and cross coupled coefficients. Okay. All right. And so how does a thermocouple work? So, it's essentially you are generating voltage, right. So, this voltage so at small enough temperatures is actually proportional to, these are all constants, times delta T by T. Okay. So, the voltage that you generate is proportional to delta T. As long as delta T is small, you can use a thermocouple. In fact, you will be surprised even to use even for 300 degrees Celsius rise in temperature, right. So, one can use a thermocouple quite efficiently. It is not the calibration is not that off, right. So even if I am measuring 300 degrees Celsius of temperature rise in my material or in a furnace, right. So I typically use a thermocouple to do that measurement, right. So although I said delta T should be small, this is for this derivation, but thermocouple is more robust than the derivation that I did, right. So let's put it that way. Okay. All right. So that's the Seebeck effect. Now the complementary effect of Seebeck effect is what is called the Peltier effect. Okay. This is also a thermoelectric effect. And in case of Peltier effect, so okay, so I'll come back to the thermocouples later, but so the idea is so I can do what is called Peltier cooling or Peltier heating, right. So I can reduce the temperature of my devices or materials by about 40 degrees Celsius, right. So I can get a Peltier cooling of efficiencies which are of of 40 degrees Celsius. So I have my material or I have something to be cooled. I do the magic of Peltier, right, and I recreate refrigeration, right. So I can cool down my material by doing this magic of so what I am going to explain right now, right. So it's not magic, but I am just transporting out heat, right. So I have a material and so I am transporting out heat from this material and I am putting it out of my Peltier, what is called heat pump, right. So I'm transporting heat. So I'm throwing away the heat from material. So in some sense I'm throwing away heat from material and thus I can refrigerate the material. Or reduce its temperature, right. So Peltier refrigerators are available now, right. So they are just small on chip refrigerators where you can put a sample and then you can just cool down up to 40 degrees Celsius. You can also heat it, right. So the heat pump can work in opposite way where you can put heat into the material and heat it, right. So increase the temperature of the material, right. So Peltier cooling and heating is a very important product in markets nowadays, right. So you can just buy a small Peltier cooler and you can do experiments at minus 40 degrees Celsius or so on and so and around, right. So 40 degrees less than room temperature. If I just want to do experiments at 0 degrees Celsius, whereas so my room temperature is 25 degrees Celsius, I don't want to put them in what are called these cryostats where I put in liquid nitrogen and then I transfer all my heat to liquid nitrogen so as to cool the chamber, right. So typically I have some sort of a vacuum chamber where I put in some liquid nitrogen, I flow some liquid nitrogen, right. Now the heat from here gets transferred to the liquid nitrogen and that is how this chamber gets cooled. I can essentially cool this down to about 77 Kelvin, that is the melting point of liquid nitrogen, right. But the point being so that is the temperature at which liquid nitrogen exists as liquid, right. So below 77 Kelvin. But so I don't have to go through all this struggle if I have a small Peltier cooler and but my desire or my experiment would require me to work only at 0 degrees Celsius. Okay. So no need for nitrogen cooling. Or even worse, helium cooling, right. So I can just do what is called Peltier cooling, right. So I can just put my device on a Peltier cooler or heat pump, my device will be speaking to the Peltier heat pump, and Peltier heat pump will suck out the heat, right. So, this will suck out heat from my device. And it is ready to use at 0 Kelvin, sorry 0 degrees Celsius, not Kelvin. Okay. So, I have some interesting phenomena happening at 0 degrees Celsius, I can just use a Peltier cooler, or even a heater. I want to see what is happening at 100 degrees Celsius. I don't need to use furnaces and other things or hot plates, I can just use a Peltier heater. Okay. Okay. So, how does this work? Now, let us go back to our Onsagers formulation again. So this is the formulation for a heat pump. So, again I have two different materials, this is A and this is B, something like a PN junction. We will not talk about PN junction today, but this is like a PN junction. You can have a PN junction instead of two materials, right. So, this is B and I connect voltage source to B. Okay. So, this is A, that is B. So, I am actually from my material I am sending heat in here, right. So, the heat that I am sending in now has two channels, it can go through this way, it can go through this way, right. So, heat in I am just going to write it as J equal to JQ, that is transporting through B, minus JQ, that is transporting through A, right. Now, what is transporting this heat? Now, okay, so the other thing that I will assume is I am going to do this isothermally. Which means my point 1 and point 2, which were earlier in the Seebeck discussion, these were at different temperatures, but here T1 equal to T2, right. So, that is my isothermal. Okay. So, that is to simplify the problem. Essentially, I do not need to do it isothermally, but if I do it isothermally, I am going to make delta T equal to 0. Okay. So, I do not have a thermal driving force for heat transport. So, heat is only transported by electric force, right. So, that is nothing but del phi or voltage, So, in other words, electron transport, electrons are carrying heat from the cold end from the material and disposing it off in the heat bath. So, I have some sort of a heat bath here. Okay. And that is refrigeration, but here I am very smartly using electrons to do refrigeration. I am not using all these gases and cycles, Carnot cycles, etc. to do refrigeration. I am just using material, right. So, where electrons carry heat, right. So, it is the electric current that is carrying heat, and this is nicely explained through Onsagers theory. So, this is the heat I put in, and for some steady state, right. So, I need to remove the same heat from here. So, the heat that is removed from here will be equal to JQ A minus JQB. This is heat removed, this is heat put in, or the power that is put in. Okay. All right. So, now let us write everything. What is J E okay, minus L E Q A, again we have delta T by T, right. So, minus L E E A delta mu or gradient of mu E A. Okay. So, I am going to just write delta T equal to 0. So, I am not even going to write all the thermal terms. Okay. So, I will just ignore this, right. So, what is J E of B? That is equal to minus L E E B delta mu or gradient of mu B and chemical potential of electrons. Okay. So, similarly J Q of A will be this time minus L E Q, which is the same as L Q E, right. So, that is the reciprocity, but that does not matter, del mu E A, right. And J Q of B will be equal to minus LEQ of B delta mu EB, right. So, now we are going to send constant current, right. So, constant current is sent through both the wires, right. So, I connect a battery and then send constant current. JE is constant electronic or charge current is sent, right. So, if I have constant charge current, I am just going to, so let us say I have a charge current of I, right. So, if I am driving current of I, then so I have delta mu E of A is just, so if I am driving constant current I, so I am looking at the potential difference that occurs in this wire versus this wire, both of them have different conductivities, right. So what is the gradient of mu E, that is just I, actually it is not, or J, so J by E L E E A, right. So, that is equal to E L E E B times del phi, right. So, or the voltage or the electric field, right. So, I am just writing what del phi is, right. So, in some sense del phi, let us put it that way, okay. So, now that is also equal to, this is J by E L E A A, that is also that is del mu, okay. So, sorry, del mu E B, let's just write no E, okay. So, del is J E by J E is a constant, right. So, J E is constant by L E E B, right. So, these are actually different values. The voltage drop that I will have from 1 to 2 in A across this resistor is different from the voltage drop across the B resistor, right. So, it is equivalent to me having A resistor and a B resistor. I am sending in current through these two. So, the voltage drop here will be I R1 and the voltage drop here will be I R2. So, that is what I have calculated here. So, this is the voltage drop or voltage drop per unit length, right. So, that is J E by L E E A and here J E by L E E B. It is a very simple calculation, okay. All right, that then, so now I have what is JQA. JQA is minus LEQA times, so this is by LEEA, right. So, del mu E is written in terms of JE by LEE, right. So, JE, and similarly JQB is equal to minus LEQB by LEEB JE, right. So, JQA by minus JQB is the heat that I am throwing out, right, and that is equal to, so how much heat am I throwing out? That is just proportional to the current that I am sending times this Onsager coefficient, right. So, EQA EQB by EEB minus LEQA by LEEA, right. So, I need to use two different materials ideally. If I use the same material, I am not going to throw out any heat, this will be 0. If A equal to B, A and B are the same material, then no heat is thrown out, right. I need to use two materials where LEE and LEEA and LEEB are different, A, and then the Seebeck coefficients are also different, right. So, in some sense, so this actually gives me the Seebeck coefficient. If I look at what my Seebeck coefficient is here, yeah, so that is LEQ by LEE, that is related to by Seebeck coefficient, right. Now, so this is Seebeck coefficient, the first Seebeck coefficient minus the second Seebeck coefficient of B minus Seebeck coefficient of A, right. So, this is related to the Seebeck coefficient of B minus Seebeck coefficient of A times JE, right. So, I can just measure the Seebeck coefficient and get the Peltier heat that is thrown out, right, from the material. Now, I can so I can make Seebeck coefficients, right. So, if I take this to be an N type material, and this to be a p type material, right. That is why I use p-n junctions typically. So, this is p type, this is n type, and I use p-n junctions for my Peltier cooling. P-n junctions are used for Peltier cooling. Right. So, then I am actually this quantity is going to be S A, which is S B, which is a positive quantity, minus S A, this is a negative quantity, right. So, in some sense, or minus S A is a positive quantity, right. So, in some sense I am adding two positive numbers. So, I will get a larger Peltier heat disposal. So, I will get a larger heat disposal, right. So, so that is the rationale for using different types of carriers, right. So, when I make these junctions, right. So, the Peltier junctions. Okay. So, so that is the, those are the thermoelectric effects. So, I am so now you understand how much heat is thrown out of the material. So, I can calculate what is the cooling that the material will undergo, right. So, that is again a thermodynamic principle, but so this is how I am actually generating Peltier refrigerators or Peltier heaters, right. So, I do not need to so if this entire thing is negative, or so if the heat that I throw out is negative, that means I am actually putting in heat into the material, right. So, I can either heat or cool. I need to just select my p-n junction in such a way that I either remove the heat, I do the refrigeration, or I put in heat where I do the heating, right. So, it depends on what I want to do. Okay. So, I can have Peltier heaters and I can also have Peltier coolers. Okay. So, so with that let us actually conclude this part, this module of kinetics, right. So, where we have seen a basic framework of all the dissipative properties, right. So, all the dissipative properties such as resistance, or conductance, let us call it conductance, the thermal conductance, creep, the Seebeck, the coupled properties such as Seebeck coefficient. Then by that we also looked at certain examples of how thermocouples are made, how Peltier coolers and heaters work. We looked at electromigration, right. So, which is another coupled property that comes through what is called carrier wind force. We looked at piezo resistance, we looked at so all sorts of thermal creep, and so on and so forth, electrical creep and so on and so forth, right. So, all these are dissipative properties, right. So, all these dissipate energy, the ds dot, right. So, is dissipated. Okay. Now, in the next module or in the next class, we will actually see, so I am saying okay, dissipation means there should be flux, right. So, of charge carriers, let us say. Whereas so if I what sort of flux, so I'm sort of confining myself so far to applying forces that are kind of static, right. So my electric field is a DC electric field, it is not some time varying electric field, right. So in a DC electric field, if I do not have any flux, right, if I just have charges that have gone and accumulated on plates, I said okay, that is susceptibility, then I am storing energy, right. Okay, good. Then I am actually polarizing my materials and storing energy in the form of polarization of the material. Now, I apply the same DC electric field, and rather than polarizing the material, I start actually moving charges around, right. So, these are free charges that are moving. Then I say this is resistance, it is dissipating, right. So, in the static scenario, I said if there is a flux, then I have dissipation. If there is no flux, or if my initially so I pull the material, I just extend the spring and the spring is there, right. Rather so I in a mechanical scenario, I extend the spring is there, I release the spring comes back, right. Rather in a plastic deformation case, I apply a constant force and the spring keeps expanding. So, there is a flux of the strain, right. So, or flux of dislocations. So, that is the difference between so what is the equilibrium case and the or the thermodynamic properties and the non-thermodynamic properties, right. So, typically however, we do these experiments not by applying static forces, right. So, we actually apply some sort of sinusoidal forces, these forces vary with time, right. So if forces vary with time, of course, you know, so if I apply an electric field that is oscillating, my capacitor will charge discharge, charge discharge, charge discharge, right. So several times along with the electric field that is charging and discharging it, right. So then I am actually creating, again I am creating some sort of a current, oscillating current, right. So why is that not flux, right. So I am not talking about flux in that scenario, right. So in that scenario there is a different way of, you know, looking at what is a conservative property and what is a dissipative property. However, both these properties, right, relate to some sort of motion of charge, right. So in case of you know, susceptibility, right. So if I am you know, so if I apply an electric field, if I oscillate an electric field, polarization keeps oscillating up and down, right. So that means I am putting charges, removing charges, putting charges, removing charges on the metallic plate. Similarly, if I apply current, if it is resistive, right, I am moving charges, this time in what is called a different phase, but again these charges are moving up and down, right. So one resistor is dissipative, the capacitor is non-dissipative, right, but both of them fundamentally the dynamics are about moving charges, right. So the question is, from the next class onwards we will see that fundamentally the underlying mechanisms for you know, so look like, you know, so at a bigger level, at a coarser level, both for dissipative properties and for conservative properties. If I am doing this constant AC measurements, then it looks like the both charges are moving, right. So what charges give rise to capacitance, what charge motion gives rise to resistance, both of them are have some sort of dynamics, it is all charge dynamics, right. So the question is, are these related in some way, right. So we are going to ask that question. I have dissipation of electrical energy, I have you know, storing of electrical energy. One comes from susceptibility, the other comes from you know, resistance or conductance, right. Is there some framework that will relate these two properties? Is it possible to know the conductance completely and then predict the capacitance, or is it possible to know the capacitance completely and then predict the conductance, right? These are the questions that I am going to ask from the next class onwards. So we have to go more into the dynamics, right. And this static picture is going to change from now on. So we will bring in the frequency dependencies, we will bring in the time dependencies of all properties and so on and so forth, okay. So now we are going to, so far we have seen dissipative as different, conservative as different properties, right. So now we are going to unite them and then bring them you know, together and say that actually they are you know, part of the same coin, right. So we are going to do that from the next class onwards, okay. So I will see you again in the next class. Thank you very much. Bye bye.